Tonight, we're exploring one of astronomy's most peculiar choices. A unit called the Parsec, that almost no star actually sits at, yet it appears in every professional research paper about the cosmos. By the end, you'll understand not just what it is, but the fascinating story of how a measurement choice made in 1838 still dominates astronomy today. If you enjoy these explorations, a like or subscribe helps. Now let's begin. Imagine you're an astronomer in 1837. You stand at your telescope night after night, staring at a faint star called 61 Cygni. You know Earth is moving through space, orbiting the sun at tremendous speed. You know that if you're patient enough, precise enough, careful enough, you might detect the star's position shift ever so slightly against the background of more distant stars. And if you can measure that shift, you'll accomplish something humans have been trying to do for 2,000 years. You'll measure the distance to a star. Friedrich Wilhelm Bessel did exactly that. What he couldn't have known was that his measurement would create a unit of distance that would still dominate astronomy nearly 2 centuries later. A unit that makes no intuitive sense to anyone outside the field. A unit that marks no natural boundary in space. A unit based purely on the geometry of his measurement technique. The Parsec. For most of human history, stellar distances were a complete mystery. Ancient Greek astronomer Hipparchus, around 130 BCE, catalogued over 1,000 stars. He measured their positions carefully, tracked their movements across the sky, recorded their brightness. But distance? He had no idea. His best guess was that they sat on a crystal sphere beyond the planets, all equally far from Earth. This wasn't stupidity or lack of imagination. It was the best explanation fitting available observations. The stars appeared to be fixed points of light that never moved relative to each other. They kept perfect formation night after night, year after year, century after century. The ancient Greeks actually had a word for this celestial sphere. They called it the firmament, from the Latin word meaning to make firm or strengthen. The idea was that the stars were literally embedded in a solid crystalline sphere that rotated around Earth once per day. This sphere sat beyond the planets, which the Greeks knew moved against the stellar background. They had tracked Mars, Jupiter, and Saturn carefully and watched these wandering stars trace complex paths through the constellations. But the stars themselves never budged relative to each other. Aristotle, writing in the 4th century BCE, argued that this celestial sphere must be made of a 5th element, different from the earth, water, air, and fire found below the moon. He called it ether, or quintessence. This substance was perfect, unchanging, and eternal. The stars embedded in this sphere partook of its perfection. They never changed brightness, never appeared or disappeared, never moved except for their daily rotation with the sphere itself. This model made sense for 2,000 years because nobody had instruments capable of detecting stellar parallax or proper motion. The stars really did appear absolutely fixed. Every observation confirmed the model. When Ptolemy compiled his great star catalogue around 150 CE, documenting over 1,000 stars and their positions, he found the same patterns Hipparchus had seen 3 centuries earlier. The constellations hadn't changed shape at all. For 2 millennia, nobody did better. The technology simply didn't exist. Telescopes were eventually invented in the 1600s, and they revealed astonishing details about the moon, planets, and stars. Galileo saw mountains on the moon and 4 moons orbiting Jupiter. He discovered that the Milky Way consisted of countless individual stars, but he still couldn't answer the fundamental question of how far away anything was. the stars appeared absolutely fixed. If something doesn't move, you can't triangulate its distance. You need to view an object from two different positions and measure how its position changes. That's how your brain perceives depth. Your two eyes see slightly different views of the world, and your brain uses that difference to judge distance. Close one eye and reach out to touch something. It's harder because you've lost that depth perception. Your brain needs the parallax between your two eyes. For stars, we needed something similar, but on a cosmic scale. Human eyes are separated by only about 6 centimeters. That's enough to give depth perception for objects a few meters away, but utterly useless for anything at astronomical distances. We needed a much larger baseline. By the 1600s, scientists had figured out a clever idea. Use Earth's orbit around the Sun as your triangulation baseline. Johannes Kepler had established that Earth orbits the Sun in a roughly circular path. By the mid-1600s, astronomers had measured Earth's orbital size fairly accurately by observing transits of Venus across the Sun's face. They knew Earth orbits in a path about 300 million kilometers in diameter. That's 186 million miles. This means that in January, Earth is on one side of the Sun, and 6 months later in July, Earth is on the complete opposite side. Observe a star in January. Note its exact position against the background of more distant stars. Then observe the same star in July from the opposite side of the orbit. You're viewing from two positions separated by that full diameter. It's like having eyes separated by 300 million kilometers instead of 6 centimeters. Even the nearest stars should show a tiny shift against the more distant background stars. This shift is called stellar parallax. Measure this shift, use basic trigonometry, and you can calculate the distance. The concept is beautifully simple. Draw a triangle. The base is Earth's orbit diameter. The vertex is the star. Measure the angle at the star and you can calculate how far away it is. Simple geometry that any student learns in school. The execution, however, proved nearly impossible. The problem was that the shift is incredibly tiny. We're talking about angles smaller than 1 arcsecond. To understand how small 1 arcsecond is, imagine dividing a degree into 60 parts. Each part is 1 arcminute. Now divide each arcminute into 60 more parts. Each of those is 1 arcsecond. So 1 arcsecond is 1/3600th of a degree. To give you a physical sense of this, if you hold a tennis ball at the distance of 1 kilometer, the ball appears about 1 arcsecond wide. If you're standing on a beach and you see a ship on the horizon 10 kilometers away, a person standing on that ship's deck appears about 1 arcsecond tall. That's the kind of precision 17th century telescopes would need to detect stellar parallax. They couldn't do it. The best telescopes of the time had mechanical wobbles larger than the signal astronomers were trying to detect. Atmospheric turbulence blurred images by several arcseconds. Temperature changes made telescope parts expand and contract by amounts that threw off alignment. Even the astronomer's own heartbeat could introduce vibrations large enough to ruin measurements. The foundations of observatory buildings settled and shifted with temperature. Wind pushed on telescope tubes. Robert Hooke tried in 1669. He was a brilliant scientist, one of England's leading experimentalists. Hooke had contributed to optics, mechanics, astronomy, and biology. He coined the word cell after seeing the structure of cork under a microscope. He formulated Hooke's law of elasticity. He was a serious scientist tackling a serious problem. Hooke built a special telescope mounted in a tall building to minimize atmospheric distortion. The idea was that mounting the telescope high up would put it above some of the turbulent air near the ground. He observed a bright star called Gamma Draconis for months, took careful measurements, detected what he thought was a shift in position. He published his findings, claiming to have measured stellar parallax at last. He was wrong. What he had actually detected was something called stellar aberration, a different effect entirely that comes from the combination of light's finite speed and Earth's motion through space. Here's how aberration works. Light travels at finite speed, about 300,000 kilometers per second. Earth is moving around the Sun at about 30 kilometers per second. When you point a telescope at a star, you have to tilt it slightly in the direction of Earth's motion to compensate for the fact that light is traveling down the tube while Earth is moving sideways. It's like running through rain. Even if the rain is falling straight down, you have to tilt your umbrella forward because you're moving horizontally. This aberration effect is real and measurable. But it's not parallax. Parallax makes nearby stars shift against distant background stars. Aberration makes all stars shift in the same direction by the same amount. Hooke had discovered something real and interesting, just not what he thought he'd discovered. The actual discovery of aberration is credited to James Bradley in 1728, who figured out what was really happening. William Herschel tried a different approach. Herschel was the astronomer who discovered Uranus in 1781, the first planet discovered in recorded history. Before Uranus, humanity knew 5 planets, Mercury through Saturn, all visible to the naked eye and known since ancient times. Herschel's discovery of a 6th planet made him instantly famous. He reasoned that if you observe double stars, pairs of stars that appear close together in the sky, one star in the pair might be much nearer to Earth than its companion. If so, the near star should show parallax, while the distant one doesn't. Over many years, he made thousands of painstaking measurements of double star systems, carefully tracking the angular separation between the components of each pair. He never found parallax. But his work wasn't wasted. He discovered that many double stars aren't just chance alignments, 2 unrelated stars that happen to lie along the same line of sight from Earth. They actually orbit each other gravitationally. He had discovered binary star systems, pairs of stars bound together by gravity, orbiting their common center of mass. This turned out to be one of astronomy's most important discoveries. Binary stars became crucial tools for measuring stellar masses. By watching how fast 2 stars orbit each other and measuring their separation, you can calculate their masses using Newton's laws. This is still how we measure most stellar masses today. Herschel's failed attempt to find parallax led to a discovery that transformed stellar astronomy. By the early 1800s, measuring stellar parallax had become astronomy's great challenge. It was the Holy Grail. Everyone knew it should be possible in principle, but nobody could actually do it. The failure wasn't from lack of trying. Dozens of skilled astronomers across Europe spent years on the problem. Some claimed success, publishing measurements that other astronomers couldn't replicate. The claimed distances varied wildly, suggesting the measurements weren't reliable. The distances were too great, and the measurement too difficult for the instruments of the time. Friedrich Wilhelm Bessel was different from his predecessors. He was German, born in 1784 in the town of Minden in Westphalia. Interestingly, Bessel didn't start out as an astronomer. He began his career as an accountant for a trading company. But he taught himself mathematics and astronomy in his spare time. He was particularly interested in navigation and studied how to calculate positions using astronomical observations. At age 20, Bessel calculated the orbit of Halley's Comet using old observations. He did this purely as a hobby, But his work was so good that a professional astronomer, Heinrich Olbers, noticed it and helped Bessel get a position as an assistant at a small observatory. By age 26, Bessel was appointed director of a new observatory being built in Königsberg. He would spend the rest of his career there, making it one of Europe's leading observatories through the quality of his work. Bessel became one of the most meticulous scientists of his generation. He was obsessed with precision and error analysis. This was still a time when many scientists took measurements somewhat casually, writing down whatever their instruments showed without carefully considering all the sources of error. Bessel was different. He didn't just take measurements. He analyzed every possible source of error, built mathematical models to account for them, and repeated observations until he was absolutely certain of his results. He studied how atmospheric refraction changed with temperature and humidity. Air acts like a lens, bending light that passes through it. The amount of bending depends on air density, which varies with temperature, pressure, and water vapor content. Bessel made extensive measurements of these effects and developed correction formulas. He measured how his telescope's metal parts expanded and contracted with even small temperature changes. A brass tube might expand by a millimeter or more with a 10-degree temperature change. That sounds small, but it's enough to throw off the precise angular measurements needed for parallax. Bessel attached thermometers to his telescope and measured its length at different temperatures, developing correction factors. He tracked the mechanical play in his mount, the wobbles in his building's foundation, even the effect of wind pressure on the observatory dome. Every possible source of error was studied, measured, and accounted for. This level of care was unusual for the time, and is exactly what was needed to detect parallax. In 1837, Bessel decided to tackle the parallax problem directly. He chose his target carefully. He picked a star called 61 Cygni, located in the constellation Cygnus the Swan. It wasn't particularly bright. In fact, you need a small telescope to see it clearly. Under dark skies with good vision, you might barely glimpse it, but most people would miss it entirely. It's what astronomers call a fifth magnitude star, at the limit of naked eye visibility. But 61 Cygni had one crucial property that suggested it might be relatively close to Earth. It moved across the sky faster than almost any other star. This motion isn't parallax. It's called proper motion, the star's actual movement through space over time. Most stars have such small proper motions that they appear fixed even over human lifetimes. The constellations look the same now as they did to ancient astronomers, but a few nearby stars have measurable proper motion. Bessel reasoned that a star with high proper motion was probably relatively nearby. Think about watching cars on a highway from an overpass. The cars on the near lanes seem to zoom past, while distant cars barely seem to move. Same principle applies in space. Nearby stars moving at typical stellar velocities show larger proper motions than distant stars moving at the same speed. 61 Cygni has one of the largest proper motions known at the time, suggesting it was a nearby star and therefore a good parallax target. From August 1837 through August 1838, Bessel made hundreds of observations using a specialized instrument called a heliometer. A heliometer is essentially a telescope with a split objective lens. The front lens of the telescope is cut in half, and one half can be slid sideways relative to the other. This creates two images of whatever you're looking at. By adjusting how much you slide the lens, you can superimpose the two images or separate them by precise amounts. This design lets you measure tiny angles with remarkable precision. If you're measuring the separation between two stars, you can put one star image from